Okay, so this is the YouTube link. Yeah, so Amok, that's perfectly fine. If you don't have a webcam, that's completely fine. I mean, but the vast majority of people have webcams, so you should show the world who you are instead of being shy about it. And, well, anyway, that's just my opinion. I might be wrong. So, all right. So last time, so in the past 3 classes, right? I've like done a lightning review of Newtonian mechanics. I've talked about like equations of motion, Newton's laws, and several examples of solutions of those laws, right? So now I think we are ready for special relativity. Okay, but before I begin the relativity portion, so see. Let me ask you all, do you have any questions about what we have discussed so far? Okay, all right. So now we've been talking a lot about physics, right? Now let's talk a little bit about philosophy. Okay. What is philosophy? Anybody knows? Any philosophers in the audience? At this age, everybody is a philosopher. Ah, yes, Abhay.
Plato, Greek philosopher, Plato.
Plato.
Yeah, Plato.
This is Plato, like Deccan Plato. This is Plato, like the philosopher. Okay. Okay, shouldn't. Just joking. Okay. Everybody has different pronunciation. My wife has a pronunciation which is very different from mine. So, so Plato is a philosopher, right? That's right. Aristotle is a philosopher. But these are all philosophers, right? What do philosophers do? What is philosophy? What is it? What does this mean? Philos and Sophie, right? Who is Sophie? Anybody knows?
Yes, sir.
Who is Sophie?
First human robot, मतलब humo.
Now somebody will say that she was the first sheep to be cloned. No, that was Lucy.
Sophie is robot.
Dolly, sir. So that was Dolly.
Huh?
Dolly.
Huh?
Dolly. That was Dolly, sir.
Dolly.
That was
Dolly. Dolly the sheep. See, you all know it so much better than I do. So who is Sophie? The first cow to be cloned or something like that? No. Sophie is a goddess of truth. Okay. And or it might be Sophus. So again, my knowledge of Greek is also very good. Philo means, what does philo mean? You know, hydrophilic, hydrophobic. What is the meaning of hydrophobic?
Fear of water.
fear of
water.
Phobos means what?
Fear.
And philos means?
Like
attracted
to water.
Something to love, to like,
love.
to pursue, right? So philosophy means the pursuit of truth, right? The pursuit of knowledge. That's what philosophy means. So And what is physics? Does anybody know the original term for the word physics?
Study of natural phenomena.
Natural is right. Natural philosophy. Right? That is what. So you have heard of Newton, right? Newton was this guy 400 years ago, 450 years ago, right? He wrote a book, right? What did he call it? Introduction to Physics. Huh? What did he call it?
Principia.
Principia. Principia means what? Principia. Principles. Principles of what?
Physics.
Principia of the Mathematica. Principle of the nature.
Principia Mathematica. What Mathematica means? What? Software? No, right?
Language of
mathematical principles. Principia Mathematica. Philosophy Naturalis. Right? This was the name of his book. It means mathematical principles of natural philosophy. Right? This is the book where you can say that physics first came into concrete existence. Right? So physics is the science of, and natural is a study of natural phenomena, right? But philosophy is an integral part of that, right? It is not. This is not engineering, right? This is in engineering there is very little philosophy, right? I mean, well, there can be, but not in the way that we are generally exposed to it, right? So the philosophical basis of physics is what? Is the first of all, it's the knowledge that, okay, we can understand the world that is around us, right? And that we can make this understanding, we can express it in the language of mathematics, right? So this understanding is of what? Understanding is of objects, of systems, and the interactions between objects and systems, right? Now, what do objects do? What is the most fundamental thing that? So, what is the most fundamental thing that any object or any system does?
Occupy volume.
Occupy volume. Actually, that's very good. That's a very very, I mean, nice observation. But when I say does, the word does is there, right? So occupy volume is right.
Some interaction with the surrounding.
So to do something, what is the word that is used when some
energy, sir, energy transfers or takes energy.
The word is, well, I mean, you can use many different words. Any of those words will do. The word that I'm looking for is motion, right? So motion is the most fundamental. I mean, motion is the most general kind of change that any system or any object can undergo, right? So physics began as a study of motion, right? And you can say that geometry is the study of static objects. For example, something that occupies volume, how does it occupy volume, and so on and so forth. Physics began as a study of, well, what happens when things start to change, right? When the shape of something starts to change, when the volume that something it occupies, that changes, right? So motion, right? And motion, this is what Newton's achievement was, right? He gave a mathematical description of motion. So for that purpose, he invented the differential calculus. He said that, well, you can define this quantity, right? And then you can do all kinds of things with it. So there was the whole mathematical thing, but then there were certain assumptions that he made about the motions of moving bodies, right? One of the assumptions is that the state of motion, right? That the state of motion of any object depends on the observer, right? Now, Newton did not explicitly state it in this way, okay? This is called the relativity principle, right? It says that the state of motion of any object, right, depends on the observer's frame of reference. So, as a very simple example, right? If you look at a train, all right, inside this train, there is a child. The child is playing with a ball, okay? The child is bouncing the ball on the floor of the train. Fine. Now, there is somebody sitting in the train, okay? What is the trajectory of the ball as seen by this person sitting inside the train?
Linear.
According to this person, the trajectory of the ball looks like this.
Linear.
Right? So you would say that x of t is 0 and y of t is some periodic function of time, right? Y of t is some periodic function. Y of t is equal to y of t plus delta t. It's a periodic function. Now you take this train and you put this whole train in motion, right? But when we say motion with respect to what? Motion with respect to some observer, right? There is some observer. Let me call this observer O prime. Let me call this observer O. So O prime, with respect to O prime, the train is moving
Rightwards.
right, whichever direction, right, left, whatever, some direction, it's moving with some speed v. What is the trajectory of the ball as seen by this observer?
Parabolic type.
Parabolic.
Parabolic.
Well, parabolic or something like that, right? But it's not a straight line. It goes like this. Right? So the state of motion of this object is different. It depends on the observer who is looking at it. Right? And if you want a more precise way of stating this, we would use the notion of transformation of coordinates. So you have one frame. So we will speak of frames of reference and we will draw frames of reference in this way, okay? As a pair of axes, one axis is a space axis, the other axis is a time axis. Okay? This is an observer, okay? And what is this C? This C is something which has dimensions of speed. Okay? Some speed. It's can be anything. It doesn't matter. It can be 1 meters per second or 10, 20,000. Why is this C? Because if I take dimensions of C and T, what do I get? What is the
Distance.
dimension of C multiplied by T?
Meters or centimeters.
L, right? Distance, which is equal to the dimensions of position. So just to make the dimensions on both axes the same. All right. So this is the observer A, right? And we have some object at some position X in this observer's frame of reference. Okay. And then there is another again observer as O prime. Now this observer's X coordinate, I put a prime, and the observer's T coordinate also I put a prime, right? So now the thing is that if you start from the relativity principle, right, then how do you define an observer? You define it as a some set of coordinates, right? X, Y, Z, and T. So, I mean, if you didn't have any preconceived notions, you would think that another observer, second observer, would be given by some other set of coordinates, X prime, Z, Y prime, Z prime, and T prime, right? But what happens in Newtonian physics? In Newtonian physics, time is the same for everybody, right? Now, this comes from an assumption in which Newton himself made. Okay, so when he was writing this Mathematica, Principia Mathematica, so he, let me see if I can, what he said, let me see if I can find it. What was his statement? So if you go to the, if you just search for Newton on time on Google, you get the Wikipedia page on absolute space and time, okay? So this is what he said about time. He said absolute, true, and mathematical time flows without regard to anything external, okay? And so basically, essentially what he's saying is that time is the same for all observers. Right? But then he also said about the same thing about space. He said space is also absolute and it is immovable, right? So he, and then he said, well, relative space and relative time are defined with respect to different observers. So in Newtonian physics, you have delta t prime is delta t. You also have delta x is equal to delta x prime is equal to delta x. All intervals are the same. Okay. But all coordinates are not the same. So for instance, in this observer's frame of reference, this object, which is at this coordinate, x, could be in a different, so I'll write it as x naught, could be in a, will be in a different location, x naught prime, right? And x naught prime will not be equal to x naught, right? It just, because it depends on this, it depends on this observer's definition of what where the origin is, right? And the sense of orientation of the axis, right? So if you are in more than one, if you consider more than one spatial dimension, then for instance, one observer's axis could look like this, right? They could be rotated relative to each other. They can be translated, they can be rotated relative to each other. they can also be moving with respect to each other. Right? So let's take this frame of reference, okay, and let's set it in motion with respect to O prime. All right. So now one can ask, what happens to the position of this point as seen by O prime? Right? So you have some object, let me just call it P. Position of P with respect to O is x naught, right? And it's a constant. But the same position with respect to O prime, what is it? It's equal to I will write it like this: x prime is equal to x naught prime plus v naught times delta t. Right? X naught prime is the position of this object in O prime's reference at some initial time. And as time proceeds, this observer moves to the right, right? And so this position changes by an amount given by v naught delta t. So we would write this expression in this way, that now if we assume that the origin of both of the observers is aligned at the time whatever the initial time is, okay, the origin is aligned, then you would say x prime is equal to x plus v delta t. X is the position of whatever is the object here, and since the axes are aligned at the time t is equal to 0, it's also the position here. And then at a later time, this whole frame has shifted to the right. So at a later time, this has shifted by an amount which is equal to v delta t. Right? So this is called a coordinate transformation. Okay. Now, what if you are in we live in 3 dimensions, right? As far as we can tell. So in 3 dimensions, let's say there is a point P which is located at x, y, z. Okay. And in frame of reference, O. Okay. O is moving with some velocity v. Okay. And what is v? V would have some components vx, vy, and vz, right? Prime. Right? Because this is the velocity of motion of O with respect to O prime. You have to keep this in mind. So these components are with respect to the prime coordinate system. Right? What is this velocity in O's frame of reference?
Sir, y prime reference, sir, vx prime, vy prime, vz.
So what is v? V is the velocity of this observer, right? With respect to this observer, right?
Understood.
What is your own velocity as seen by you?
Vy
It's zero,
Zero.
right?
ऊपर नीचे कर रहा है.
It's your own, because you are in your own frame of rest frame.
Yes, sir. Yes,
So
sir.
this velocity has to be defined with respect to this observer, right?
Yeah, understood.
With respect to O prime. Then what happens to the coordinates of this point P? As coordinates x prime,
X plus V.
X plus Vx prime delta t.
right?
Yes.
Y plus V. Vy prime delta t.
So I'll put this as x naught prime, y naught prime, and same thing for z. This way we don't have to assume that the origin is coincides at some initial time. Okay. So this is the origin. This is the location of the point at the initial time, right? In the O frame of reference. So this is and this is called a Galilean transformation, by the way. Okay. And we give it a name because later on we will be looking at a different kind of transformation, right? The transformation that was used by Einstein, but that transformation was first discovered by a gentleman by the name of Lorentz. So that's called a Lorentz transformation, right? So we'll be looking at Lorentz transformations later. So we call these Galilean transformations to distinguish them. You might ask, well, why don't we call them Newtonian transformations? I don't know, maybe because Newton already has everything named after him, right? And Galileo also did a lot of work prior to Newton, right? Galileo studied the relative motion of objects, right? He looked at falling objects, for instance. The famous Leaning Tower of Pisa experiment. Whether he did it on the Leaning Tower of Pisa or not, we don't know, but right? So that's why it's one reason why it's referred to as a Galilean transformation. Now, okay. Now we can ask what happens to other quantities. This is for position, right? This is how position transforms from one coordinate system to another coordinate system. Okay. So now we can ask, well, what happens? What if in this frame of reference, okay, X in CT, what if I have an object that is moving? Now, how will I represent a moving object in this picture? Can you tell me? One axis is position, one axis is time. So how will you represent a moving object?
Hyperbola.
Hmm?
Like the x-axis is distance, y-axis is time, right, sir?
Right.
Comes in a hyperbola.
Well, it will be any straight line. I'm talking about constant velocity. Right. So any straight line which has some non-zero slope. Right.
Yes.
So if I look at a straight line, what is the slope of this line? It's C delta
T by delta x.
and this is delta x, right?
Yes.
So the slope of this line, right? The slope of this line, m is equal to tan theta is equal to c delta t by delta x, which is equal to c by v, right? Vx. We call this beta, 1 over beta x. So beta is defined to be v by c. And if I look at one particular component, it's written as Vx by C. Okay. Again, we are using these definitions because this is what happens when we go to relativity, right? So we have the advantage of foresight. We know where we are going to go. So you have some object that is moving with some speed v or Vx, right? And this is the speed of the observer of this object with respect to O. All right. Now I have O prime. Okay. And I can ask the same question, that O prime, that O again is moving with some speed v naught with respect to O prime. What is the state of motion of this object as seen by O prime, right? So let's look at this thing, coordinate description, right? So x prime, right, is equal to what is it equal to? Let me write it down more carefully this time. Let me say that the origin of this coordinate system as with respect to O is at x or x naught prime, and then the location of this object is at x naught plus x. Okay, x is the location of this object with respect to O. X naught is the relative displacement of the origin, right? And now what is this x prime is a function of t, right, which is equal to v naught delta t, right? But now the thing is that this x is also a function of t, right? So I can differentiate both sides with respect to t. Okay. But you might ask, why don't I differentiate with respect to t prime? Right? Because delta t is equal to delta t prime. Right? So normally I should do this, but instead I just do this. Okay. So when I do this, what happens? X naught is constant, right? Whatever the original position was.
Zero.
Plus dx. Sorry, this is just zero. Right? Sorry.
Yes.
0.
Plus dx by dt plus v naught. Right. So what is the speed of this object as seen by the observer O? It is equal to Vx plus V naught. Right. I mean, right now we are looking at a one dimension. But by the same reasoning, right? When you go to more than one dimension, what do you get? You get, now I can write this as a vector equation, right? X prime is equal to x naught, the relative location of the origin of O with respect to O prime, the location of the point with respect to O, plus vector V delta t. So now I can take the derivatives of all of these. Now, every time I'm writing this expression first, dt prime, just to remind ourselves that this is actually what we should be doing. So this speed I'm calling v naught, the relative speed. Right? So this is the
Vectorization.
Galilean transformation of velocities. We refer to this as Galilean velocity addition. You can also call it velocity subtraction, but it's the same. Okay. Very often you will see the opposite. V is equal to V prime minus V naught. Right? So this is what happens if you look at the same object, right, from the perspective of O. So now you put the object in O prime's frame of reference, and you say in O prime's frame of reference the velocity of the object is V prime, and then you say that your own frame of reference is moving with respect to O prime with a speed V naught. What is the object in your velocity of in your frame of reference? It's V prime minus V naught. Right? So these are both complementary sides of the same picture. Right? So this gives us the how velocities transform. Now what we can ask the same thing about momentum. What about momentum? Momentum goes like this. P is equal to mv. Right? So now I can ask, well, what happens to the momentum of the object with respect to the other frame, mv prime? Right? Now again, we should say m prime v prime. Why? Because if the state of motion of the object depends on the observer, then all of the properties of the object should depend on the observer, right? Or they can. They don't have to, but they can. But assuming that the mass does not change from one moving observer to another, again, doing this tells us that again we have an assumption about the mass. We get m is equal to v naught, this, plus mv naught. So what do I find? I find that the momentum is equal to the momentum of the object in the original frame of reference plus this guy, right? What is this? This is the momentum. We will call this the center of mass momentum. Okay, you will see why. Right? Now, what about Newton's law? We have to ask ourselves, is Newton's law the same as seen by O prime? So what is Newton's law in O frame of reference? This is Newton's law as per O. What will be Newton's law as per O prime? Well, Newton's law will be this quantity as per O prime, right? Now we have to ask ourselves the question. When I transform from P to P prime and from T to T prime, right? So when P goes to P prime and T goes to T prime, right? I should ask this question. Is it true that dP by dt becomes dP prime by dt prime? Right? Because if it doesn't, then what is the state? Then it means that Newton's law is being modified with respect to this observer, right? And if Newton's law is modified, then that means that by comparing the result of two experiments, one done by O and one done by O prime, right? O can determine the state of motion of their system, or conversely, O prime can determine the state of motion of their system. We'll come to this later, okay? But let's see first of all whether this is the same or not. So we start with this expression, right? So P prime is equal to
P plus P naught.
P plus P naught. So now we take derivatives. dP prime by dt prime. But now I know that dt prime is equal to dP prime. शशांक मैं आपको म्यूट करने वाला हूं क्योंकि थोड़ा सा बैकग्राउंड नॉइज है आई थिंक ओके यू कैन अनम्यूट योरसेल्फ इफ यू वांट टू आस्क एनीथिंग ओके dP prime by dt prime which is equal to dP by dt plus dP naught by dt. ठीक है? So now if dP naught by dt is equal to 0, right? Which means that the relative velocity is constant. Okay? Then F prime is equal to F. Right? But if dP naught by dt is not 0, and instead dP naught, this is something else. So this is instead this is something else. Let's say MA or MA naught. Okay. Then what is Newton's law? It is modified. F prime is equal to F plus MA naught. Okay. Now this thing has a certain interpretation. Let's say that F is 0. Let's say the force on the object as seen by the observer O. So let's say the force on this object as seen by the observer O is 0. Okay. So this object is moving at some constant velocity or is at rest with respect to O. But now O starts to accelerate, right? V naught is not constant. So O starts to accelerate with respect to O prime. Okay. So when it starts to accelerate, what happens? As seen by O prime, right? As seen by O, there is still no force on the object. But as seen by O prime, right, it appears that the object has some force, which is given by m times a naught. Right? So this force is there purely as a consequence of the relative state of motion, right? So this is called a pseudo force. Okay, so we'll talk more about pseudo forces a little bit more. We'll talk about it in the next class. Okay, so today we have talked about this thing. We've talked about relative motion. We talked about the principle of relativity and the transformation of velocities, positions, momenta, and forces. Okay. Questions?
Sir, there P naught or V naught is the, if that is V naught is velocity of O prime, no sir, with respect to O prime. V naught.
V naught is the velocity of O with respect to O prime.
Yeah, done.
Now, when you look in textbooks, you'll find that there are some sign differences because of the way that they treat the relative observers. Okay, so you can look at the same. You can look at the same thing in a different way. You can put this object in O prime and then ask, what does a moving observer see? Right? So it's the same problem. I have put the object in a moving frame and I'm asking what is an observer see in this moving frame. Normally what you will find in the textbooks is that this object is put that this frame is kept at rest and this frame is moving, right? Then you will get an equation x prime is equal to x minus v delta t, right? But that is exactly the same as what I'm doing, because if you take this observer to be moving with some speed v naught to the right, that is equivalent to taking this observer moving to the left with some speed minus v naught, right? So I'm getting x prime is equal to x plus v delta t, right? There you will see something like x prime is equal to x minus v delta t. It's just a different labeling of primes and the observers, okay? But both are identical situations. And in fact, this is what is the principle of relativity. This is an example of the principle of relativity. Okay, any questions? Okay. All right, then I'll see you all tomorrow.